So, we've investigated Atwood's device before. As you know, this larger object is going to accelerate down, and the smaller object is going to accelerate up. But this time, we're going to investigate it using energy ideas instead of forces. So, what type of energy do we have before, and what types of energy do we have after? Let's take a look. Before, nothing is moving, so there's no kinetic energy. This object has potential energy. I'm going to call that object 2. And that's it. This one here is sitting on the ground, or what we call 0. It has no potential energy. After, we're going to let this thing go, and it accelerates. It goes faster and faster. Right here, this object is moving, and it's above the ground. So it has both potential energy and kinetic energy. Oh, that's still object 1. Get the right subscript. There we go. This object is down here at what we call ground level, so it has no potential energy, but it does have kinetic energy. It is moving. The law of conservation of energy tells us the energy before equals the energy after, so we can just write the equation. The potential energy of object 2 before equals potential energy of object 1 plus kinetic energy of object 1 plus kinetic energy of object 2. You remember from the other day, we talked about potential energy, that is mgh, but we got to be careful. This is mass 2, so that is the that's this object right here, the before picture. Let's see, over on this side of the equation we have mgh, this is object 1. Kinetic energy is 1/2 mv squared, this is object 1, and 1/2 mv squared, object 2. You'll notice I didn't put subscripts with the velocities because they're both moving at the same speed. Again, here, when we talk about energies, these are scalar quantities. So even though this one's going up, it only has a certain amount of energy, and there's no direction associated with that. So the velocity of this one and the velocity of that one are essentially the same. Let's see here. You might remember sometimes we can cancel out masses, but that's not the case today because these are different masses. So we're going to need to leave those guys in here. Let's do a little bit of algebra. Let's rearrange this equation. What I'm going to do, let's separate. Let's put everything that has V on that side and everything that doesn't have V on this side. So over here, I'm going to subtract m1gh from both sides. But I'm going to use the distributive rule right away to pull out the gh. So it's going to be m2 minus m1 inside parentheses times gh. We're going to do the same thing over here. We're going to leave this stuff, but I'm going to use the distributive rule. Let's write it this way. We'll pull the 1/2 out front. We're going to write m1 plus m2. We're going to leave that in the middle, and v squared at the end. Let's see, the only thing I need to do yet is, multiply both sides by 2, divide both sides by the total mass, and take the square root. I'm going to do that all in one step and turn it around at the same time. So this becomes 2mgh all over the total mass, and we take the square root of the whole thing. Very nice. At this point, we plug in some numbers and see if we can arrive at an answer. And as you can see there, we end up with a final velocity of 1.25 meters per second. We could check that if we went back and used the Atwood device equation that we derived in an earlier chapter. Remember, acceleration equation? Then we would have to use some kinematics to find out what that velocity is. I bet we would arrive at the same result. Very interesting. Law of conservation of energy applied to Atwood's device.